Let us talk about rational functions in their graphs. Our goal is to be able to graph these rational functions. We need to know something about the domain, also vertical and horizontal asymptotes. And you recall the idea of finding the X-intercept and the Y-intercept, that they come into part here in terms of trying to determine, graph the rational function. We can identify slant isotopes, and then from there, the goal would be to graph these rational functions. You recall that the domain of a rational function is the set of real numbers except when the denominator, that is that q of x here, defined from this equation or this function, when that denominator is equal to 0. We want to exclude those values. So a rational function is just a function in fractional form, something divided by something else. Here, for example, we want to talk about the domain. And when you look at this first function for f of x equals to x squared minus 9 divided by x minus 3, we tend to think that you can just look at that denominator and set it equal to 0, and you get x equal to 3. And let's start by saying x minus 3 equal to 0. And so that implies that x is equal to 3. Well, x equal to 3 becomes a problem. But for f of x to really be exact with how we do that, you need to factor that numerator if you can, of which we can. That's divided by x minus 3. Notice the x minus 3's cancel out. And so all we have here is this line x plus 3. But we have a hole at x equal to 3 because of the original function. We had x minus 3 equal, well, x minus 3 in our denominator. You set that equal to 0, and that implies the problem child, x equal to 3. So we exclude x equal to 3, and we talk about all the other numbers on the number line. So we break the number line up based on this critical value for x. We look at from negative infinity to that 3, and then that's union from 3 to positive infinity. So the parentheses around the number just simply means that we do not include that number, that endpoint, but we include all others. That's a negative in there, right? For part B, obviously, when you set this denominator equal to 0, you get x equal to negative 3, x equal to 3. Excluding those two values, and we used to write the domain like that. So two ways you can write them in terms of set notation. Or here, the interval notation. And so that's the domain there. Just rehashing things that we've talked about, even going back to chapter 1. Now for part C, you look at, again, as in fractional form, something divided by something else. So the critical part is always what's downstairs. Now the question is, can x squared plus 9 equal to 0? So if you set that denominator equal to 0, what you end up with is something strange. You get x squared equal to negative 9. Well, that's impossible. How can I square something and that result comes out to be negative? Well, that's impossible. Well, you know that's impossible because if you keep on solving, take the square root of both sides, you get x equal to plus or minus 3i. So that's imaginary. So we don't have any real values for x. So for this one, there is no x value such that x squared plus 9 is equal to 0. So we say that x squared plus 9 is never equal to 0 for all x that's real. We get two values in the imaginary. We get x values in the complex set, right? Namely, x equal to minus 3i and then x equal to positive 3i. But that's imaginary. They're not real. So here, our domain for part C would be all real numbers, right? Everything going from negative infinity to positive infinity. We want to be able to graph this function f of x equal to 1 over x. And I'm kind of skipping some of the concepts, but I want to kind of embed this in your mind. Notice that we cannot divide by 0. So division by 0 is not allowed. So this implies that x cannot equal to 0. So our domain is from negative infinity to 0, union from 0 to positive infinity. Now notice that x cannot equal to 0, so that means that we don't have a y-intercept. Remember, the y-intercept is when you set x equal to 0. So no y-intercept. Now if you set the function equal to 0, you set f equal to 0. This implies that you have 1 over x equal to 0. We're going to solve for x, multiply both sides by x. If you can see what's happening, we're not going to get an x-intercept either. So we get x times 1 over x is equal to 0 times x. Well, this implies that 1 is equal to 0. Well, that's impossible. Well, that's impossible, then that means no x-intercept either, right? We talk about something called vertical isotope and horizontal isotopes. The vertical isotope is when we look at those x values when our denominator is equal to 0. And they become vertical lines. So here, since that x cannot equal to 0, that becomes a vertical isotope. X equal to 0 is a vertical isotope. The horizontal isotope, now the vertical isotope means, is there a vertical line that the graph does not cross, that it tries to ride up? It wants to cross over it, but we have typically a number that's undefined, and so it doesn't know what to do, so it goes to either plus or minus infinity. It blows up in outer space. And the same thing happens sometimes horizontally as well. Now I'm going to define in detail the idea of the vertical isotope and the horizontal isotope just in a little while. For this problem, we have the horizontal isotope is the line y equal to 0. Now, why is that? And I want to go over that just a minute. But here's what's happening. What happens to this so-called function as these so-called x values as they get large? What happens when x gets large? When x goes to infinity? Well, 1 over x goes to some horizontal isotope, if it exists. And here, this horizontal isotope would be 0. what happens to f of x when x gets large. Here, no restriction, without bound on x. So that becomes this idea of a limit of 1 over x as x goes to infinity. Well, this guy goes to 0. So this horizontal isotope is a limit, right? So this says, what is the limit of the function as x approaches infinity? Well, as x gets large, 1 over x gets small, right? So like, say for example, 1 over 10 is 10, right? 10. 1 over 100 is 100. Now this, the so-called, I'm going the wrong way. Oh, that's for the so-called vertical asymptote. So we have this 1 over 10, 1 over 100, 1 over 1,000, 1 over big numbers. These numbers are getting closer to 0. So now let's look at the number line and partition the number line based on the critical x values. So partition the number line based on X-intercepts if possible. Sometimes you don't have X-intercept, like for this problem. In vertical isotopes. We only have one vertical isotope, that was x equal to 0. So we look at from negative infinity to 0, and then from 0 to plus infinity. We want to determine the sign here to determine the signs, let's say sign of each interval. So we're going to test the number. Let's say test -1 here. Let's say we test 1. I try to always pick easy guys. F of -1, plug that back into the function, right? So that's just -1. The sign is negative. That's all I'm concerned about. So it's negative. And then we test f of 1. That's 1 over 1. That's positive. Okay. So negative means under the x-axis. Positive means above the x-axis. So now I'm ready to graph. Have the x-axis and the y-axis. So this vertical asymptote is the line x equal to 0. Well, the line x equal to 0, that's just the y-axis, right? And this horizontal asymptote y equals 0, well, that's just the x-axis. So we have these asymptotes, this vertical asymptote here, x equal to 0, that's the y-axis. Asymptote means that the graph wants to cross, but it can't, so it rides along with it. Asymptotic nature simply means there's some kind of limitation going on. That is, the graph continues to travel in a particular direction that's approaching the so-called asymptote. And then y equals 0 is the x-axis. So you go from negative infinity to 0, the graph is here under the x-axis, and it rides along with the asymptote. Isotope there and there. And that's always negative because it's below the x-axis. Then you go from 0 to positive infinity. The graph is positive, it's above the x-axis. Find the asymptote and you got the graph. That's the basic rational function. This is the basic rational function. Let's keep digging. Definition of the vertical asymptote. We look at, if there's a vertical line and the graph is trying to cross it, but it can't, what are those values for x? They're just the numbers of x when that denominator was set to equal to 0. But you want to make sure that you reduce the quotient. If you need to factor the top and the bottom and cancel some terms out, make sure you do that. And then you set the denominator equal to 0 and solve for x. These x values are called the vertical asymptotes. They were those critical numbers for the domain, those values that you excluded. Now you know why you're excluding them, because they're vertical asymptotes. The graph never crossed there because the graph doesn't exist at those values. So those values become hot areas, hot topics, right? You think about it. These vertical, horizontal asymptotes remind us of this imaginary line, the border of Russia and Ukraine. Who wants to cross it? Well, somebody just did, and you can see what's happening right now. So look at this first illustration. As x approaches a from the right, that means that plus sign means as I'm getting closer to a from the right, that's this way. What happens to the graph? The graph shoots up into heaven, right? And then what happens as x approaches a from the left? That's from this way. X gets close to a from the left. It also shoots up into positive infinity. The third illustration, what happens as x approaches a from the right? This guy goes downstairs. It goes into the abyss, negative infinity. That denotes asymptotic nature, vertical asymptote. Find the vertical asymptotes, if any, of the graph of each rational function. Well, you want to reduce, that is simplify, factor if possible, and then look at your denominator. Well, we can factor here, but it's still going to stay the same. Look at our denominator. You said x squared minus 9 equal to 0. We can factor there. So we get x equal to 3, x equal to negative 3. These are our vertical asymptotes. For this one, for g, we had better factor. because I looking at something that's common for the top and the bottom. There it is there. So g of x is 1 over x minus 3. So you only said x minus 3 equal to 0. And that implies that x is equal to 3. So our vertical isotope, and I just use VA, for vertical isotope, is the line x equal to 3. Then over here, x squared plus 9, that denominator is never 0. That was the first illustration. I'm sorry for being redundant. Is not equal to 0 for all x. So that means no vertical isotope. Now for the horizontal isotope, again, is also a limiting factor going on. What happens to the function when x goes to infinity? Right? So when x goes to infinity, that is when x blows up. This is going to plus infinity. Here, the y values get close to this imaginary horizontal line. Here, y equal to b. So y equal to b then is said to be a horizontal isotope. Now, how do you get that? We look at locating horizontal isotopes. You're going to look at 4 things. You're going to look at n, which is your degree for your numerator. Then you look at m. This is our degree for the denominator. I'm going to compare those 2 numbers. If n is less than m, if our degree in the top is less than our degree in the denominator, then automatically your horizontal isotope is y equal to 0. See, I did that back on this problem that I was doing here. See, this is how I got y equal to 0 for a horizontal isotope. Now, if you don't see an n in the numerator, look, our m downstairs is 1. That's x to the first power. That numerator is 1 times x to the 0 all over x to the first power. Because you recall, x to the 0 is just 1 anyway. So this means that our n is 0 and m is 1. So I get n less than m. Automatically, the horizontal isotope is the line y equal to 0. Okay. So I was just going by that rule. If n equal to m, then the horizontal isotope is the ratio of the leading coefficients. The leading coefficient is this number, a sub n times b sub m. There's no subscript in the number. They're just saying that's just the number associated with the term for the highest degree or the highest power. So if n equal to m, then the horizontal isotope is the ratio of the leading coefficient. Ratio means just fraction, right, or quotient. If n is greater than m, if the degree of the numerator is greater than our degree in our denominator, then the graph has no horizontal asymptote. If that degree differs by 1, that is, if I look at n and m, if they differ by 1, that is, if n is greater than m by 1 number, then we talk about a slant or a slanted isotope. I think if your country, we put an ed on slant. We talk about slanted isotope. I like that. That sounds closer to home to me. All right. So we look here at this problem. You're looking for the horizontal isotope. So notice that n is equal to 2 and m is equal to 2, right? That's n and that's m. So since they're the same, then our horizontal isotope is the ratio of the leading coefficients, 9 divided by 3. That's y is equal to 9 over 3. That is y is equal to 3. So y equal to 3 becomes that horizontal imaginary line. Now for this one, n is equal to 1 and m is equal to 2. So I get n is less than m. That implies that the horizontal isotope is automatically y equal to 0. Over here, n is equal to 3, m is equal to 2. So I get n is greater than m. So that implies no horizontal isotope. Okay. Now here are my steps to graphing rational functions. See if you can find the x and y intercepts if they exist. Find the vertical isotope if they exist. Find the horizontal isotope if they exist. And if they don't, let's go out here and pick some cucumbers and watermelons, right? If the function does not have a horizontal isotope, determine if the function has a slant isotope. Now, for the homework, I didn't put slant isotopes there. I have probably, I think, an example that comes up. I make mention of it, but then we'll move on. I'm not going to test you on slant isotope. Kind of figures a lot to get anyway, and so why keep adding stuff? So if we can get the basics, I think we have succeeded. Step 5, partition. That is, divide the number line based on the x-intercept and the vertical isotopes to determine the sign of each interval. And then after that, graph the dang on rational function if you can. All right, so we're going to graph f of x equal to 1 over x squared. And I may be out of order. That's fine. Let's get the vertical isotope. Vertical isotope is found when we set our denominator equal to 0. That implies that x equal to 0. And that's our vertical isotope. For the horizontal isotope, if the degree of the numerator is less than our degree in our denominator, which it is, 0 is less than 2, then automatically the horizontal isotope is the line y equal to 0. Now the line y equal to 0 is the x-axis, undercover, and the line x equal to 0 is the y-axis, undercover brother. So we got that. Now, do we have a x-intercept, y-intercept? No. Now, I'm not making it up. What's f of 0? Remember, that's how you find the y-intercept. That's 1 over 0. That's undefined. So here, there's no y-intercept. So we find the x-intercept, we set the function equal to 0. That is 1 over x squared equal to 0. Well, that implies that you multiply both sides by x squared, you get 1 equal to 0. I don't want to go to hell. No. Okay. So that is no x-intercept. Partition a number line based on these x values. Have the number line goes from negative infinity to positive infinity. Well, those critical x values is that x-intercept. Well, I'm sorry, the vertical isotope. There is no x-intercept, but we get the vertical isotope is x equal to 0. Now this graph is always positive. Look, 1 is positive forever, and x to be squared is always positive. So you can check the points you want, but you're going to get positive values always. That means that the graph is always above the x-axis, right? I mean, you go in there and plug in numbers if you want. That's fine. So f of negative 1 is 1 over negative 1 squared. That's 1. Positive is what we want. And then f of 1 it's just equal to 1 over 1 squared. That's just 1. Again, positive is what we want as well. So our graph, let's label the horizontal and vertical isotopes. So for that vertical isotope, we get the line x equals 0. That's the y-axis. And then for the horizontal isotope, we get the line y equals 0. That's the x-axis. There's no x-intercept, no y-intercept. So the graph never crosses the x-axis. I'm sorry, the graph doesn't, the graph doesn't cross the x-axis, neither does it cross the y-axis. No x-intercept, no y-intercept. Yeah. So the graph is always positive. So that means from negative infinity to 0, the graph is in the second quadrant. And then from 0 to positive infinity, the graph is in the first quadrant. That's where it's positive, right? And it hovers always close to the isotopes. Okay. Now, they'll talk about symmetry, and I didn't make mention of that, but there is symmetry going on. You can look at that as symmetry with respect to the y-axis. So we look at symmetry in terms of what happens with f of negative x. If that gives us f of x, then we say it is symmetric with respect to the y-axis. And if we have f of negative x is equal to negative f of x, then it's said to be symmetric with respect to the origin. And if none of that happens, then it's not, there is no symmetry, right? So that is, there's no symmetry with respect to the y-axis or the origin. So for this problem, if we plug in a negative x, we get 1 over negative x, all to be squared. That's just 1 over x squared. Well, that's equal to the original f of x. So this is symmetric with respect to the y-axis. Well, duh. Well, look at it. I get the mirror image on the left and the right side. So that's the idea of the symmetry. Sometimes if you can graph it, you can see. Oh yeah, just a note here for the basic one, f of x equal to 1 over x. Watch this. F of negative x is equal to 1 over negative x. That's negative times 1 over x. That equals to negative times f of x. So this guy is symmetric with respect to the origin. Now how does that look? Well, remember that the basic graph remember this basic graph was this. So it's symmetric with respect to the origin. And that's what that means. You remember this problem here, this is not a rational function, but it was symmetric with respect to the origin as well too. Look at how that guy goes. Right? So symmetric with the origin means that the graph is going to be in the first and third quadrant together or second and fourth quadrant together. Right? If it's symmetric with respect to the y-axis, then the graph is going to be in the first and second quadrant or the third and fourth quadrant together. Now, we know the graph of 1 over x squared. We just did that guy. So that was this. Now, this has a shift. This is a vertical shift up. One, and this is a horizontal shift. That's x minus 2 equal to 0, x equal to 2. Horizontal shift to the right. By 2. And what's happening? Let's go deeper. When you see the problem like this, it's kind of already telling you this guy right here is going to be the horizontal asymptote, y equal to 1. And then this is telling you denominator set that equal to 0, you get the vertical asymptote, x equal to 2. Okay. So what you're going to do is just remember from whence this graph g of x, that function comes from. It comes from f of x. It takes f of x, it just shifts it up 1 and shifts it to the right 2. So I'm gonna go up 1, then I'm gonna shift to the right 2, and then just draw that graph, that same graph. Okay. Well, that's good stuff. This idea of the slant asymptote, if the degree of the numerator is 1 degree more than the degree of the denominator, then you have what's called a slant or slanted asymptote. And what is it? Well, to do that, you just divide. So we always divide the bottom into the top. We're missing a 0, so we insert a 0 there. X goes in x squared, x times x is x squared. X times -1 is minus x. Draw a line, subtract, that becomes negative, becomes plus. Now this 0x is just 0. It's just there for a pivot position. Bring down the x, bring down the 1, divide x into x, that goes 1 time. 1 times x is x. 1 times -1 is -1. Draw a line, subtract, that becomes negative, becomes positive, remainder 2. So in this division, we have here this function, and this is f of x, is equal to x plus 1 plus 2 over x minus 1. So that term there is always the slant asymptote. Okay. So that's what that is. Let's say, for example, if you were graphing that, notice that the vertical asymptote is x equal to 1, right? The horizontal asymptote, the degree of the top is bigger than my degree downstairs, so there's no horizontal asymptote. But there's a slant asymptote because the degree is off by 1 from the top to the bottom. So we have a slanted asymptote. And that is y equal to x plus 1. I got it from here. Okay. Partition the number line based on these critical X values. Now, we have to find, we got the we got the vertical isotope, but we don't have the X-intercept. So let's see if we can find the X-intercept. X-intercept means set the function equal to 0. So I have x squared plus 1 over x minus 1 equal to 0. Multiply both sides by the denominator, so I end up with x squared plus 1 equal to 0. That gives me x squared equal to negative 1. No x value, no real x value. How about that? So there's no X-intercept, no real X value. Now we're looking for the X-intercept, and for the Y-intercept, X-intercept we set y equal to 0. To find the Y-intercept, we set x equal to 0. So we get 0 squared plus 1 over 0 minus 1, so that we end up with negative 1. So 0, negative 1 is the Y-intercept. So we divide the number line based on the critical X values, which is only 1, and that was that vertical isotope X equal to 1. So this numerator is always positive. Right? Check an X value squared, positive plus a positive value, positive plus positive is always positive. That's for the numerator. Divided by, now here, the values change when X is less than 1, right? What happens when X is less than 1? So if you take a value, let's take 0 and plug 0 there. Plugged in 0, we got negative 1. So we get negative values over there. Take a number bigger than 1, then that denominator, let's take 2. Then we get a positive value, right? So let's label the vertical isotope. That's the line x equal to 1. Let's graph the slant the slant isotope. That's the line y equal to x plus 1. So here the y-intercept is 1, and the slope is go up 1, go over to the right 1. So like, well, that was 1 there. So go up 1, go up to the right 1. So here, all right. So we have what we need, and so we have an intercept when x is 0, y is negative 1. That's here. So when I go from negative infinity to 1, this graph is negative. It's below the x-axis. So, but it's looking for the isotopes. It has the intercept, then it drops back down. And then from 1 to positive infinity, the graph is positive. From 1 to positive infinity, the graph is positive. That means that the graph is either here, there, right? So where is it? Well, check this out. It can't be here because it has no isotope this way. It has an isotope here, isotope there. But if it's going to do that, if it's going to do this, then that means down here becomes negative. Right? That's impossible. Because it says from 1 to positive infinity is positive. So it's not there. Now, check this out. So it can't be here, because if it's here, again, it has to ride with the isotopes. But there's no isotope over here and over there. So what's it going to do? Right? It's just going to go crazy? No, no. Math does not act like people, right? So again, this is 1, right? X equal to 1. So is it here? Well, let's say if it's here, then we're saying, okay, it has to ride with the isotope there and there. That's fine. But does it cross down there? No, because it's always positive, right? It doesn't go back that way. This is not an isotope. So no, that's not it. So the only place it's positive from 1 to positive infinity, from 1 to positive infinity, right? From 1 to positive infinity is in this section. And there is bounded by isotopes, and it's positive, right? And this is the graph. Make it black. That's it. Let me get that out the way. Find the domain. Again, set the denominator equal to 0. Solve for x. And so you get x equal to 7, x equal to -7. And you exclude those values because we cannot divide by 0. And that's how you write your domain. Here, we're going to find the vertical isotopes. It's interesting. Set our denominator equal to 0, so I get x equal to 0 and x equal to -9. There's no holes. Holes means cannot divide the numerator and denominator and cancel a factor. If I cancel something out, that meant that there was a hole there somewhere, right? So all I have is 2 vertical isotopes. Find the vertical isotopes here, but be careful, right? Because notice that I can cancel out. I can divide an x. This is x divided by x. So all I have left is just 1 over x minus 9. 1 over x minus 9. So I only have one vertical isotope. That's x equal to 9. But the hole that I got rid of was at that x equal to 0. But we got rid of it. So the vertical isotope is x equal to 9. And then the hole corresponds to x equal to 0 that we divided out. Right? Find the horizontal isotope. Here the power up top is 1 and our degree downstairs is 2. So I get n is less than m. So that implies that the horizontal isotope is the line y equal to 0. For this one, when the degree in the numerator is the same as our degree in the denominator, n is equal to m. This implies that the horizontal isotope is the ratio of the leading coefficient. Y is equal to 32 over 8. You just get 4. So this is just y equal to 4. Find the horizontal isotope, if any, of the graph of the rational function. Here, n is 3, m is 2. N is 3, m is 2. So here we have n is greater than m. So no horizontal isotope. Right. Do we have an isotope? Yeah. And what is it? Wouldn't you say it's a slant? Because the degree up top differs from the degree downstairs by 1. So we have a slant isotope. Okay. All right, so here's the big guy. So follow the 7-step strategy to graph the following rational function. Is it symmetric? We talk about if it's y-axis symmetric, you got to have f of negative x equal to f of x. If it's symmetric by the origin, you got to have f of negative x is equal to negative f of x. And then if neither of those work, then you say that is neither. So we're going to just plug in f of negative x, replace x with negative x. This is negative 2x. This is all over negative x minus 5. Okay, and so this is negative 2x all over negative times x plus 5. So then the negatives cancel out. We have 2x over x plus 5. Doesn't look nothing like the original, so it's neither, right? Because that x plus 5 downstairs, right, throws us off. Now it says, does it have a y-intercept? To find the y-intercept, set x equal to 0. Let x equal to 0. So this implies that we have f of 0 is equal to 0 all over negative 5. I can divide by 0 by negative 5, I get 0. So the y-intercept is 0. Is there an x-intercept? For the x-intercept, we set the function equal to 0. Set f of x equal to 0. Solve for x. So we have 2x all over x minus 5 equal to 0. Multiply both sides by the denominator, you end up with 2x equal to 0. And that means that x is equal to 0. So x equal to 0, and it says just put the number in there. So x equals 0 is the x-intercept. So the x and the y-intercept are the same, the origin, right? So now find the vertical isotope, same problem. So here we set the denominator equal to 0. We get the vertical isotope x equal to 5. You got to put in x equal to 5. Find the horizontal isotope. Look at the degree of the numerator, the degree of the denominator. They're the same. So the horizontal isotope, n is equal to 1. That's equal to m. That means that implies that the horizontal isotope is the line. Sorry, I didn't write that. You didn't see that. Is the line y equal to the ratio of the leading coefficients, 2 divided by 1, which is 2. So that's y equal to 2. So you got to put in y equal to 2. Now for me, all I was concerned with for this last step where they plot points, my steps just simply say just divide the number line based on the vertical isotope, which is a 5, and the x-intercept, which is 0. And then you find the signs. Is it positive, negative, positive, whatever, right? They're doing the same thing by plotting the points, all right? They're doing the same thing by plotting the points. Here you plug in x. These are the x values. Plug in x to equal negative 7. And so you're going to solve. So you have f of negative 7 is equal to 2 times negative 7 all over negative 7 minus 5. So you get negative 14 all over negative 12. But that gives you positive 7 over 6. And so I've done that, right? Do that for each of those numbers and plug those numbers in. So they want you to find the sign. So look, I'm looking for a number less than 0. Well, that would be this negative 7 is less than 0. So the sign that I get from here is positive. See that? It's positive. That's all I'm concerned about. Matter of fact, negative 5 is like that, and we get positive. So I'm going to put plus sign there. Now pick a number between 0 and 5. They did that with the 2. They get negative. Pick a number greater than 5. They got the 6 and the 7. They're both positive. See that? We're ready to graph. All right, so here's the graph. And again, I just use my partition, but they got you for my math lab plugging in these dang on numbers. That'll make you, man. You'll see what I'm talking about when you do that homework. You'll come back the next day. You'll be frowning at me. I know why. But anyway, the vertical isotope is the line x equal to 5. We had a horizontal isotope at the line y equal to 2. We had intercept here at the origin. So when x goes from negative infinity to 0, the graph is above the x-axis. That's what that plus means, above the x-axis. So it's doing this. And then it goes from 0 to 5 is negative, is under the x-axis. The signs just tell us if it's above or below the x-axis. And then from there, you want to find the isotope, and it wants to get to the railroad track, What was that? Is that commercial, Geico commercial about those kids? They're trying to run from the Jason guy, and they're like, let's head to the cemetery. Anyway, I love that commercial, boy. So then we go from 5 to positive infinity. 5 to positive infinity. The graph is positive. And so is it here or is it there? Well, it can't be in here. Look, you got the isotope there and there, but it's not crossing. If it crosses, it becomes negative. It's supposed to be always positive over there, so that doesn't work. So where it's always positive and it's going to be bounded, that is hovering next to the isotopes, is here and there. All right. So let's go back and look at what you did. See that graph there? So let's come over here and look and see. So this guy has a vertical isotope that's negative. No. This vertical isotope is a negative x value. No. So it's between B and D. So now I got to pay close attention to the intercepts, where the graph crossed the x-axis, the y-axis, right there at the origin. Right? So the graph has to cross at the origin. Now look, for D, it's crossing at the origin, and then for B, it's crossing at the origin. But look at where the graphs are. We got to match them up. See how this graph here, this guy is doing this, right? And then it's doing that. So I come over to the answer that matches B, right? All right, we have another one. We set that up. So we determine symmetry. So I'm going to plug in a negative x. So this is negative 7x all over this negative x to be squared minus 4. This is negative 7x all over positive x squared minus 4. It's like I'm writing them upside down. 7 times negative x all over negative x to be squared minus 4. This is negative 7x all over. You square that, we get positive x squared minus 4. That's the same thing as negative times the original function. I don't need the negative there. I'll pull it out. 7x all over x squared minus 4. So this is negative times f of x. Now again, we said if it's symmetric with the y-axis, you have f of negative x is equal to positive f of x. If it's with the origin, we get f of negative x is equal to negative f of x. So this guy is symmetric with respect to the origin. See that negative there in the front, right? What's the y-intercept? We set x equal to 0. Set and let mean the same thing, right? Sit, Ubu, sit. Roof, roof, good dog. Y'all don't remember that commercial, but anyway, set x equal to 0. And so this implies that we have 7 times 0 all over 0 minus 4. We get 0 divided by -4, we get 0. So here we get y equal to 0. For the x-intercept, we set y equal to 0. That implies we get 7x over x squared minus 4 equal to 0. Multiply both sides by the denominators, you end up with 7x equal to 0. And that implies that x is equal to 0. Just put the number. Vertical asymptote, set our denominator equal to 0. You get two values, right? You get x equal to plus or minus 2. So, right, isn't this when you factor? So x equal to 2 and x equal to -2 are vertical asymptotes. You got to put x in there. X equal to 2, x equal to -2. The horizontal asymptote, here the degree of the numerator is less than our degree of our denominator. So the horizontal asymptote is the line y equal to 0. Test these numbers of the function. I did that for you. What are they trying to do? Again, I mean, could be a lot of busy work, but we'll take that. We'll take, you do that work and you get those numbers. And man, I think I was messing up. I didn't use my calculator. I trusted my brain. How good that is. So you use your your regular calculator. Partition the number line based on the X-intercept, which, you remember what the X-intercept was for this? I think it was X-intercept was 0. So 0 there, and also the vertical asymptotes, -2, +2. It's 1, 2, 3, 1, 2, 3, 4. So let's find a number less than -2. Well, that's that -7 or -6. Both values here are negative. See that? Negative. That means it's going to be below the x-axis. A number between -2 and 0, -1. +7 over 3, plus sign. It's going to be above x-axis. A number between 0 and 2, 1, negative, right? Below. A number bigger than 2. Just see how they're testing 6 and 8. Just need one of them. You get the same you get the same sign. Okay, talk better. Today is a new day. So this is plus. All right. So from there, when I was a student at Alabama State, this one professor, man, he would curse all through class. Wouldn't curse students out. He's just, and it wasn't math. I don't know if it was geometry or something. And I didn't have him. My class was like next to his class, and all the students over in his class would be laughing every 5 minutes. This guy, he put a curse word, in between every sentence, every comma, and the students thought that was funny. It's probably not funny, but their class used to wake us up, because in my class, the teacher was like, "Oh, the one, and then you right next to that class, you hear this bust out of laughter, and you're like, I wish I was in that class where the teacher is cussing. No, I'm just joking. So anyway, let's partition. This is the y-axis. Okay, I already got x there. Partition this. Find the vertical asymptote. X equal to -2, x equal to 2. The horizontal asymptote was the x-axis, y equal to 0. See if I can just on top of that put those dots, right? And then, oh, it touched down. It did cross. It went. It did go berserk. It crosses at the origin, right? Yeah. And so you get you do get, sometimes where it kind of breaks the cadence. So from, I'm looking at my number line from negative infinity to -2 is under the x-axis. Let's use different colors. So it's find the isotopes, it rides along. Then from -2 to 0 is positive, it's above the x-axis. Find the isotope, ride along with it. Then it tries to, it wants to cross the intercept. It does this. That's why from 0 to 2 it goes negative from the intercept, and then it rides along the isotopes. It's smooth there. And then from 2 to positive infinity, it's plus. It's above the x-axis, rides along the intercepts. Rides along the isotopes, excuse me, I'm getting hungry. All right. Let's see that graph. Got to pick that graph out. You see it looking up here. See if we can find it. That guy looks like it's D. Yeah. All right. Now the rest of these, I just pulled them out, and I'm just going to work them, the way I work them. And and the way I work them, look, we do it quick. So the vertical asymptote, you get 2 of them, x equal to plus or minus 1. The horizontal asymptote, here the powers are the same, so I get y equal to 6. The ratio of the leading coefficient 6 divided by 1. The x-intercept, you set the function equal to 0, and you end up with x equal to 0. So we get 0, 0. So the x-intercept and the y-intercept are the same for this particular problem. Get 0, 0. Okay. Is there symmetry? No, I don't think so. You plug in negative f of x. Well, the numerator stays the same. I'm sorry. This is x squared minus 1. It stays the same. So we get this guy to be f of x. So here we have symmetry with respect to the y-axis. Huh, pretty cool. So you see how I just blurted out before what I thought, but I didn't do the math. And so that's the thing, man. We can't just trust what we think. We got to work it out. Partition the number line based on the x-intercept, which is 0, and also the vertical isotopes, -1 and +1. Now check this out. The numerator is always positive, so I'm not checking the signs there. Now this denominator is x minus 1 times x plus 1. So I'm going to test a number on each interval. So let's say we test -2. Here we test a fraction, -1/2. Test 1/2. Test 2, right? So if I put a -2 here, again, the top is always positive. Not checking that, just checking the bottom. A -2 to be squared is 4 minus 1. I get +3, plus sign. Put that -1/2 in there, and then when I square it, I get 1/4 minus 1 negative, right? Same thing happens with the 1/2. 1/2 to be squared is 1/4 minus 1 is negative value. Check 2. Anything bigger than 1 is going to be positive for the denominator. 2 squared is 4 minus 1. I get +3. All right, let's see. So we had that this vertical asymptote, well, 2 vertical isotopes, x equal to -1, x equal to 1. and then y equal to 6 way up there. I'll just put it here. It touches down at the origin. Okay. So let's change the color for effect. So from negative infinity, right, to -1, negative infinity to -1 is plus. It's above the x-axis, and it rides along the isotopes. So it's not going to be there because there's no isotope here, right? So you find the isotopes and you ride along with that. And then from -1 to 0, from -1 to 0, it's under the x-axis, but it touches down there. So here's the isotope it does there, but then it wants to get to that intercept. And then from 0 to 1, it drops back down and it rides along with the isotope. And then from 1 to plus infinity, from 1 to plus infinity is plus, it's above the x-axis. Find the isotopes. That's it. N80, N03, B, N20, is it 20? Yeah, N23, be a little better. All right. I'll do this one and maybe another one. There's a lot of problems here, but I mean, once you get the hang of it, all the steps are just being repeated. So vertical asymptote, see that? X equal to -9. Horizontal asymptote, let's change the color. Here the degrees are the same, so I get the ratio of leading coefficients. -1 divided by 1 is -1. Okay. Put my sins and put them in a bag. Is that Job 19:17 or Job 17:19? Anyway, what about the intercepts? Well, if we let x equal to 0, I get 0 over 9. It gives me 0, right? So I get 0, 0. That's the x and y intercepts. Let's partition the number line based on here the x-intercept is 0 and that vertical asymptote x equal to -9. So we want to find some values. Find a value less than -9. Let's try -10. Let's try -1 here. Let's try 1 over there. So we try f of -10. So that becomes +10. It's already a negative there. All over -10 plus 9, that's -1. So I get, all I'm concerned with is the sign. We get negative. Let's test f of -1. That's 1 over -1 plus 9. I get 8 positive. Let's test f of 1. So that becomes -1 over 1 plus 9. That's 10 negative. Graph this. The horizontal asymptote is the line y equal to -1. The vertical asymptote is the line x equal to -9. It touches down here at the origin. All right. So from -infinity to -9, that's the isotope here, is negative. So it's under the x-axis, it rides along the isotopes. From -9 to 0, from -9 to 0 is positive. It's above the x-axis, has the intercept there though, so it does this. And then from 0 to plus infinity, it's negative. It goes below the x-axis, and it is looking for its isotope, and it rides along that. Right. And you can smooth that out and just kind of make it, like it's continuous. That's my left hand drawing. All right. Let me do one more. Just look at these. They're all cool. I think that's the last one. Yeah. So, and I love them all, right? So let's pick one more because I'm getting tired and I gotta eat something. So, well, I'll do two more. I think this one is important. So notice that x squared plus 4 is never equal to 0. Can never be equal to 0. This implies no vertical asymptote. It does have a horizontal asymptote. These two numbers are the same, so the horizontal isotope is the ratio of the leading coefficients. 6 divided by 1 is just 6. Now, if I let x equal to 0 to solve for y, I get 0 over 4. I get 0. So 0 comma 0 becomes x and y intercept, right? X-intercept, and it's the y-intercept. Okay. Oh, is it symmetric? We gotta find. I'm sorry with this color. My bad. We need something that's gonna show up. So notice that you plug in x it be negative, but you're gonna go back and square it, so you get the original function. So this is symmetric with respect to the y-axis. Partition the number line based on those critical x values. Well, there's no vertical asymptote, but we do have an x-intercept at 0. But notice that this graph, no matter what x values you put in there, it's going to always be positive because 6 is positive, x to be squared is positive, x to be squared is positive, plus 6 is positive. So positive divided by positive is positive. So this is positive everywhere. So I don't have a vertical asymptote, but I have an x-intercept and a y-intercept at the origin, and then the horizontal isotope is the line y equal to 6. So the graph is always positive. It wants to ride along the its asymptote, but then it has to connect with the intercept. So what do you get? You get the birthplace of life. All right. You didn't know that God was mathematical. I'm sorry. I'll do the last one since it's a little bit different. So this problem and there's another one, that guy right there, they kind of match up. All right. So let's do this one. You can factor that denominator, I believe. Let's try it. So this is x, and put an x here. The factors of 15 would be 5 and 3. So the question of the sign, well, the big number has to be plus because the result is plus. So this is plus here and minus. So yeah, 5x minus 3x is 2x. So good. So can't cancel out anything there, but we can extract from that the vertical isotopes. X equal to -5 and x equal to 3. Okay. Now, when you find f of -x, this gives us -x plus 2 over x squared minus 2x minus 15. This does not equal to f of x, and neither does f of -x equal to negative times f of x. So here there's no symmetry. What about the horizontal asymptote? The power here is 1, the power there is 2. 1 is less than 2, so the horizontal asymptote is the line y equal to 0. All right, so we're going to partition the number line based on the, oh, I didn't get the x-intercepts and the y-intercept. Good. So let's set x equal to 0. So that gives me 2 over -15. So this, what is this? This is 0, comma, -2 over 15. That is the y-intercept. And then we set the function equal to 0 and solve for x. So here we get x plus 2 over x squared plus 2x minus 15 equal to 0. Multiply both sides by that denominator, and that denominator cancels out. All you have left is x plus 2 is equal to 0, x equal to -2. So -2 comma 0 is the x-intercept. So divide the number line based on the vertical isotopes and the x-intercept. So the vertical isotope, we get x equal to -5, and also we get x equal to 3, and then for the x-intercept, we get x equal to -2. Looking for the signs on each interval. So I'm going to test the number, right? So let's pick -6, -3, test there. A 0 is there, and we found that when x is 0, where's that guy? We get -2 over 15, so that's negative. That's all we need, just the sign. Then let's test a number, easy numbers. I get numbers close to those values, right? So, so when you test the -6, I look at what's factored. So f of -6 is equal to -6 plus 2 is -4 over the -6 plus 5 is -1, and -6 minus 3 is -9. 3 negatives, we get negative, right? Negative divided by negative is positive, times a negative is negative. So now we test f of -3. You get -3 plus 2 is -1. -3, I'm plugging this into the factor terms. -3 plus 5 is 2. And then -3 minus 3 is -6, positive. And then we test that 4. F of 4 is equal to 4 plus 2 is 6. We get 4 plus 5, we get 10. And then 4 minus 3 is 1. That's positive. So this is the last one. I've held you long enough. So the vertical isotopes, x equal to -5. X equal to 3. Horizontal asymptote, did I find that? Y equal to 0. So that's the x-axis. And let's see, the y-intercept is 0, -2/15. So that's about right there. And then the x-intercept is x equal -2, y equal to 0. It says about somewhere there. So look at the number line. Look at those partitions. So from -infinity to, I'm going to erase what we don't need now. It kind of looks confusing. Oh, what's that? -5. So from -infinity to -5, the graph is negative. It's under the x-axis. From -5 to -2 is positive. And then from -2 to 3 is negative. -2 to 3 is negative, but it goes to those intercepts. And then from 3, right, that vertical asymptote to positive infinity is positive. Okay. That's going to do it. Well, look over that and work through it, and work some of the other problems too and see if you get it. And that'll do it, folks.